Hello and welcome to section 20. In this video we'll be going through example 1, which will look at how to find average and RMS values and then use those to calculate power for an AC signal. So something that's sinusoidal like we talked about in section 18. So previous sections we've looked at DC signals. That's what you did up to midterm. But now things can alternate, and we want to be able to calculate power, but we don't want to have to always integrate, so we'd like to figure out a way to do it algebraically. So there'll be some integration initially while we derive our algebraic form. So I've written example 1 here. Sorry, let me show it to you real quick just so you can see where it is in the handout. So it's here, and we'll go ahead and write out these equations that are above it so that we can, there. Alright, so the first piece is to find the average, or what is called the DC component of the signal. So we have this signal. So IDC or VDC is equal to, it's also equal to I average, you can call it whatever you want. It is 1 over T integral T naught to T naught plus T. So this capital T is the period. Remember, it's one cycle, so it doesn't matter as long as you start and end at the same. So I could start here, go through and stop, or I could start here, go through and stop. So it doesn't really matter as long as, start at the rise, or I could start at the where this ends and stop where this ends. So as long as you start and stop at the same point in the signal, it doesn't matter. It should be the same period. And then, so for a current, we're going to do I of t dt. So we're just going to accumulate the area under the curve. So another way to write this is just area divided by t, or area over duration. But this duration has to be one cycle. So let's do that down here. So IDC, so we could integrate this, but it's triangles and rectangles, so why not just simplify our math here? So we have this triangle, we have this rectangle. I'm only going to look at the first cycle of this thing, which starts here at 0 and ends right there. So that'll be the cycle that we look at. Everything else is just repeating, so it won't change anything. Do not include the next triangle without including the next rectangle if you keep going. So we're just going to do area over t. T for this is, sorry I didn't write it there on the page. So this is 2 seconds, and this is 4 seconds, and this is 6 and 8 and 10. So it is 4 seconds. And the area, we'll get 1/2 base height for the triangle, and then base height for the rectangle. So basically we have a triangle and a rectangle. And we're just going to add up the areas. No reason to do integration if we can just do simple geometry. You can do it if you want. 1/2 our base, that's how long it is, it's 2 seconds long. Our height is 10. For the rectangle, the base is 2 seconds from 2 to 4. And the height is -10. Sorry about the freeze there. And we're going to divide all that by 4. You plug that into the calculator, and you should find that you get a -2.5 amps. Alright, so the next thing we need to find is the RMS current. Now the RMS current, there's going to be a little bit of derivation to get to that. So I'm going to actually work that down here. So RMS current and voltage come from this desire to algebraically find power. So let's start off by writing an equation for average power. So P average looks a lot like this. 1 over t integral T naught plus T, and then we're going to have some power function, dt, but we know that power is just voltage times current, so we can expand this. To some V of t times some I of t, and then taking a dt. Now, if this goes through a resistor, we can rewrite this. So in our case, let's use I squared R because we have a current. But we could also, so remember we have I squared R and V squared over R for our for our constant current and our constant voltage, the stuff that you did previously. So let's sub one of those in. So we want to use I squared R because we're working with a current here, but it's the same kind of stuff for the other one. Integral T naught. And we will do I of t, quantity squared, divided by R. Sorry, we do not need to square the R. Just square the I of t. dt. Now, if I look at this R is constant. Integrating it's not going to do anything. I can pop it out here in front. And we get this form, which I'm going to write it this way on purpose. 1 over R, and then 1 over t integral T naught plus T, I of t squared dt. This almost looks like this, except that I need to square this, but in order to square this, I have to take the square root first. So where this is headed is I want to be able to say that P average is IRMS squared times R. So that it looks just like it did before. To make that happen, what we end up doing is we square root the inside of this and we square the outside of it. So basically they're going to cancel. But this is important because this is where IRMS comes from. It is this piece inside of all of this. That is the RMS piece. So IRMS is equal to the square root of 1 over t integral T naught to T naught plus T I of t squared dt. And you can't see that, sorry about that. So let's apply that to our equation. Oh, I guess in case you're curious, VRMS looks basically the same. Square root 1 over t integral T naught plus T V of t quantity squared dt. So VRMS will look basically the same. So you'll need both of those. So to get IRMS, what we're going to do, and you also want to remember this equation, and then there's also P average equal to VRMS squared over R. So that's also an important one. So just kind of this guy, this one, and this one are the important ones that you want to remember for RMS. To find RMS, we're going to be working with this curve up here. So we want to translate it. So let's quickly write out what that is for that cycle. So it's going to be, so if I was going to write I of t, I would have a ramp function starting at 0, and it would be 10 over 2. And then I would turn that ramp function off, so I would subtract 10 over 2 r of t, and we would do that at 2 seconds. R of t minus 2. There you go. And then I would jump down by 20, so minus 20. Okay? So we want to turn this into an integral, so we need to convert this a little bit. So what happens here is this becomes, so this is 5RT, but it's 5T UT. And then I get this other piece, which is minus 5 T minus 2 U T minus 2. So again, turning this into a U function, and then minus 20. So this first piece is what happens for this line. So we can integrate this, and then we just care about the 5t part right now. So just the 5t. So if I go write IRMS, and I'm going to do IRMS squared so I don't have to remember that square root, then it's going to be 1 over t. So this whole thing lasts for 4 seconds. So let's go ahead and grab that. And then we are going to integrate. So we're going to do 2 integrals because we have 2 different lines. So we're going to integrate from 0 to 2 for this line, and then from 2 to 4 for this line. So from 0 to 2, we have a 5t. And then from 2 to 4, so you could just look at it and say, oh, it's just negative 10. But if you ever get like a slope over here and you want to calculate it, what you can do is you can come over here and you can convert this thing. So if I convert this entire thing, I will have a 5t. So remember, all of this is on at this point for that second piece. So 5t, and then we get minus 5t as I distribute that, and then plus 10, because minus 5 and minus 2 make a plus 10, and then minus 20. And so you add all that together, and you get a minus 10. That's the function for it. So we just get a negative 10 dt. We integrate that. We get 1 over 4, and we get 5t squared over 2 from 2 to 0, plus a, plus a negative 10t from 4 to 2. Once you work all of those numbers out, you should find that you have a Actually, we did that wrong, so let's fix that. So we have to square this, and we have to square this before doing it. Because remember, this is I squared, so a pretty common mistake. So try not to do what I just did there. So IRMS squared equal to 1 over 4, and we will scratch out this and keep working. So instead, we will integrate from 0 to 2. This becomes 25t squared dt plus 2 to 4. This becomes 100 dt. And that should work out much better. You won't get an imaginary number. So then you do all of that, and you get one over 4, and then we get 25t cubed over 3 from 2 to 0 plus 100t from 4 to 2. Calculate the number there. You'll eventually get to 66.68. Now you're going to check that against the answer and be like, well, that's the wrong number. But you have to remember, we're saying that this is equal to IRMS squared is equal to 66.68. So to find IRMS, we just take the square root of that. And then you'll get the number in the answer, which is 8.16. 5. Just to keep 4 sig figs. There you go. All right. So now, that is amps. So the last thing to do is to find power through a 2 ohm resistor. So power average, if you remember, we have this equation, IRMS squared R. So we can say that it is IRMS squared times R. Our R is 2. IRMS squared, so you could say 8.165 squared, or you can just use the 66.68, which we already have. And that will come out to be 133.4 watts of power. All right, sorry about the freeze there. So hopefully that helps. If you have any questions, please let me know.